Hi everyone, my name is John Eduardo. I'm a student at the University of La Salle, and I will explain about a study of reinforced concrete columns repaired on all of four sides with cementitious mortars, and that's it. The paper describes a study carried out in the Universidad Politécnica of Valencia laboratories. A total of 18 specimens were tested, representing a group of square 20 per 20 square millimeters columns, subject to compressive axial loads. Different repair scenarios were considered in order to study the influence of the type of mortar used and the presence or absence of bonding agents between the mortar and the column of concrete. In the specimen geometry, the study consisted of the Zone 18 30-70 mm long specimens to simulate axially loaded reinforced concrete columns. The result can be extrapolated to real columns. The specimens were dog bone shaped to avoid failure in the load application zones. The central section of the specimen was 520 mm long and 40,000 square millimeters of cross section. The heads were 420 millimeters long with a cross section of 800 square centimeters. The specimen material, a low quality concrete with a 10 megapascals compressive strength, was used to make the specimens, similar to those used in previous studies to simulate the concrete in use 40 to 50 years ago. The central section of the specimen was reinforced by four 10 millimeters diameter rebars with 6 millimeter diameter stirrups every 150 millimeters. The heads were strengthened so as to be able to transmit the load applied by the jack to the center section on which the study was focused. All the reinforcements had a tensile strength of 500 megapascals. The mortars that were used in the repairs of the column are shown in these tables. As well as the bonding agent used in the study. Class R mortar mechanical properties, class R4 mortar mechanical properties, and the bonding agent mechanical properties. Test planning, monitoring, and procedure. The three of the 18 specimen tests were undamaged and designated as CC control columns. Three others were damaged and tested without repairs and designated DC damaged columns. The remaining 12 damaged on all of four sides were repaired before testing. 3 with R3 and 3 with R4 mortar applied directly to the substrate contract designated R3 and R4 columns. 6 were given a bonding agent between repair mortar and concrete designated R3B and R4B columns. The results: the specimens were instrumented with string gauge at the center of the four rebars and placed vertically on the test beds with an axial compression load applied by a 2,500 kilonewtons hydraulic jack at a constant speed of 50 km per minute. Columns R3B. The vertical cracks can be seen typical of the dry joint due to the repair being made in two phases. Smaller cracks can also be seen coinciding with the reinforced on the sides with no dry joint, and the bonding between the repair mortar and concrete can be seen to be adequate. Columns R3. The failure made is similar to the R3B, with the vertical cracks identifying the dry joints. The mortar became completely separate from the sides, to which mortar was applied in the second phase. Columns R4B. Vertical cracks were also seen here on all of sides, the most serious coinciding with the dry joints between the both layers of mortar. Unlike the previous cases, breakage was due to the failure of the mortar under compression. Columns R4. Failure was very similar to the R3 specimens with vertical cracks, marking the dry joints and separation of the mortar from the two-side repair in the second phases.